Did you know that up to 80% of a jet engine's thrust doesn't even come from burning fuel? That sounds impossible for something that famously roars fire out the back, right? But before we get into the engine itself, you need to understand one simple rule of physics that makes the whole thing work. Push something backward hard enough, and it pushes you forward just as hard. Think about a fire extinguisher going off, or standing on a skateboard and throwing a heavy weight behind you, you'll roll forward without even trying. That's it. That's the entire secret behind jet propulsion. A jet engine doesn't need magic, it just needs to shove air backward as fast and as violently as possible. Now let's break down exactly how it does that piece by piece, because the engineering here is honestly kind of insane. It all starts with that giant fan you see spinning at the very front of the engine. That fan sucks in a massive amount of air, way more than the engine could ever actually burn. Here's where it gets interesting. Most of that air, sometimes as much as 80% of it, never even enters the core of the engine. It just flows around the outside and shoots straight out the back. This is called bypass air, and it's actually the main source of thrust on most modern jet engines, all thanks to that same pushback, get pushed forward principle. So what's the other 20% of the air doing? That's the part that actually goes inside the engine core, and this is where things get intense. First, it hits the compressor. This is a series of spinning blades that squeeze that air into a much smaller space, and on a large engine, this thing is spinning at around 10,000 revolutions per minute. That squeezing makes the air incredibly hot and dense before it goes any further. Next, that compressed air enters the combustion chamber where fuel gets injected and ignited. And here's a number that might shock you. The temperature inside that chamber can hit around 3,700 degrees Fahrenheit. For reference, that's hot enough to melt most metal on the spot. Which raises an obvious question. If it's that hot in there, how does the engine not just melt itself apart? Here's the answer, and it's genuinely clever. The blades right behind that combustion chamber, called the turbine, are made from something called nickel superalloys, special metals that can survive up to about 2,200 degrees, but that's still not hot enough on its own. So engineers drill microscopic cooling channels directly through each blade and pump cooler air through them constantly, keeping the metal just below its melting point while it sits inside what's basically a controlled explosion. Now back to the main sequence. Those hot, expanding gases blast backward through that turbine. And here's the clever part most people never think about. That turbine is directly connected by a shaft straight back to the compressor at the front, so the engine is actually powering itself. The exhaust gases spin the turbine spins the compressor, and the compressor keeps squeezing in fresh air to keep the whole cycle going thousands of times a minute, completely self-sustaining once it's running. After the turbine takes what it needs, whatever's left of those hot gases blasts out the back of the engine at incredible speed, obeying that same pushback rule from the very start of this video, and that's where the other 20% of your thrust comes from. So put it all together. You've got a giant fan pulling in air, most of it bypassing the core entirely for efficient thrust, and a smaller portion getting compressed, ignited, and used to power the whole system while adding extra thrust on the way out. Now, not every jet engine is built exactly this way. There are actually a few different designs. A single spool engine uses one shaft connecting one compressor to one turbine, the simplest setup. Most modern engines instead use a dual spool design, two separate shafts spinning at different speeds nested inside each other, which squeezes far more efficiency out of the same basic idea. On top of that, you've got different engine families entirely. A turbojet, the simplest and oldest, sends basically all its air through the core, no bypass at all. A turbofan, which is what we've been describing, uses that big front fan to bypass most of the air around the core for efficiency. And a turboprop uses the turbine mainly to spin an external propeller, instead of relying on exhaust thrust at all. And that bypass ratio actually matters a lot for turbofans specifically. Engines with a higher bypass ratio, meaning more air skips the core, are quieter and dramatically more fuel efficient, which is exactly why modern airliners look like they have such huge, wide engines compared to older jets. Speaking of older jets, this technology has a genuinely wild origin story. Two engineers, one in Britain and one in Germany, were racing to invent the jet engine at the exact same time in the 1930s without even knowing about each other. The British engineer got there first with a working prototype in 1937, but struggled to get government funding. Meanwhile, the German engineer got almost unlimited support, and in August of 1939, his design became the first aircraft in history to fly purely on jet power. Military jets take this whole system one step further with something called an afterburner. This dumps extra fuel directly into the hot exhaust stream after it leaves the turbine, igniting it for an emergency burst of thrust. It's incredibly powerful, but also incredibly inefficient, which is why you only see it used in short bursts, not for regular flight. One more thing that puts this all in perspective. A large commercial jet engine is built from over 25,000 individual parts, every single one manufactured to extremely tight tolerances. And the biggest engines flying today, the ones built for planes like the Boeing 777X, can cost upwards of $42 million for a single engine. So next next time you're sitting on a plane staring out at that massive engine, you'll know exactly what's happening just a few feet from your seat. One simple rule of physics: 25,000 parts, 10,000 RPM, and temperatures that would melt the engine itself if it weren't for microscopic cooling channels keeping the whole thing just barely alive.